Hi everyone, welcome back to my YouTube channel. With me is Steve, and in this video I'm going to share with you my learning note about Elixir programming language. I've been learning this language for a couple of days and I want to share everything that I have learned with you. And the way I learned it is by analyzing a library called Veritaserum, which is a small old library, but I think it's perfect for learning purposes. It does a sentiment analysis by using event method. And I'm going to share everything that's being used in that library. So that's the scope of this video. And if you are new to the language, I'm going to briefly explain about it. So Elixir is a programming language that builds on top of Erlang. So Erlang itself is quite old technologies built by Ericsson's engineerings, and they use it to build communication systems. And Elixir was built to make Erlang a more modern programming language. With that being said, Elixirs also will be compiled to Erlang binaries. It will run on the Erlang virtual machines. Also, it's called by Beam. And Elixir is a dynamic type language with functional programming features. And how does the library works? Well, it's basically a simple algorithm. We can give the sentence that we can or do we want to analyze, and then the library will look up into the word, and if the word exists in the dictionary list, they will check that, and then for each of the word it has a score. Score can be positive, score can be negative, and it will summarize all the scores into a final score. And if a final score is a negative integers, it means that sentence is a negative sentiment. Otherwise, it is a positive sentiment. So you can check that repository in this link. And if you want to follow along with me, it's better to read that code at least once. And if you are curious about the applications, the web applications that I'm using in this video, this is called Livebook. It's like a Jupyter book. We can use it to write interactive and collaborative code notebooks. And let me share with you the outline of the video. So we are going to explain about module and functions, documentations, type specs, data types, protocol, pipe operator, metaprogramming, pattern matching, control structure, recursions, and calling Erlang functions. So without further ado, let's get started. Now let's explore about module and functions. Module. In functional programming, the application is made of collections of functions. Module allows us to organize the code by grouping related functions in one place. Based on the community style guide, the module name should use camel case and keep acronym like HTTP, RFC, and XML in uppercase. As an example, we have def modules, keywords to define the modules, following by the module's name, and then do and end, and then we can implement the module definitions in between them. In this case, I have a function called foo which just returning a string of foo. We'll take a look about functions further later. Module hierarchy. It is possible to create a nested modules, a module inside another module. In the code sample below, functions foobar, this one, calls functions bar, defined in bar module, without using the full path foo.bar.bar. When nesting like this, Elixir automatically creates an alias to the inner modules, allowing the second module, foo.bar, to be accessed as bar. If the foo.bar module is moved somewhere else, the reference to bar in the foo modules need to be updated to the fully qualified name, like foo.bar, or an alias has to be explicitly set in the foo modules with the help of alias functions. So these things called arity, we're gonna check about that later. And module name may contain dot, and the convention is to use that dot to establish a hierarchical structures. So here the example. We move the bar modules outside the foo. Because we moved that, we rename that into foo.bar. Why? Because that gives us expressions that the bar is a submodule of foo. It does nothing to do with the compiler. And then if we wish to call the bar functions just by bar.bar instead of foo.bar.bar, we need to explicitly define the alias for foo.bar like this. Use and import. Use the import keyword to call all the public functions from a certain module without providing the module path. Right, let's take a look at an example. We have a module called Veritaserum test module. So this is a module to run unit tests. And in this module, we import Veritaserum module, which means that now this module can call all functions, all public functions in Veritaserum module. As you can see here, there is a call of analyze functions. These analyze functions basically is defined in the Veritaserum module. Okay, next, use keyword. Use keyword behave similarly to import keyword, except that the imported module will be allowed to inject and run any code to the calling module. So in the code snippet, the xunit.case module will inject all modules dependency to run unit testing into the Veritaserum test modules. So be aware of using this keyword because it will inject and run any dependencies into your modules. Functions. Named functions are defined inside a module using the def keyword. And based on the style guide, we should use snake case for the function's name. And if you pay attention, there is no return keywords because the last value in the logical block will be returned. In this case, the goodbye string will be returned automatically without the return keyword. There are naming conventions usually applied to the end of the function's name. The exclamations mark will raise an exception if the function encounters an error. For example, file.read functions, it can raise an exception if the file that we're trying to read is not accessed or it cannot open the file. And by the naming convention, we should name the functions with an exclamation mark at the end of the function's name, which tells us that these functions can raise an exception. And we also can use the question mark to show that functions will return a Boolean value, either true or false. We can also make a private functions by using def p keyword. So a private function is only accessible within the same module. If our function's body only spans one line, we can shorten it further with 2 colons keywords, omitting the function's body. So instead of writing the functions like this, we can define functions in one line using this syntax. right? So comma, do colons, and the implementations in one line. So it looks more shorter. Anonymous functions. Use fn keyword to define an anonymous functions and write the function's body after the right arrow symbol. Right, so this is how we can create anonymous functions using fn keyword following by the function's parameters and the implementations in between of the right arrow and keywords. And because this is anonymous functions, we can put that functions or assign that functions into a variable. So in this example, we have an anonymous functions that accept parameter x, and it will summarize x with 1. And then we put that anonymous functions in add1 variable, and we call that add1 by using this syntax add1 dot and then branches and then the parameters or the arguments. And dbg or debug is a built-in functions that we can use to print the debug informations. And we can also rewrite the same functions using the ampersands like this. So this is called a value placeholder, and it identifies the nth argument of the functions. So instead of using fn, we can just use ampersand. Ampersand will be ampersand1 will be a placeholder of the first argument, and it will summarize that with 1, same as before. Now if we run this example, so let's wait, and those two functions will return the same result, which is 2, as expected. Capture operator. Capture operator ampersand can turn a named functions into an anonymous functions. Why we gonna do that? Because if you want to pass a function as a function argument, or if you want to bound functions into a variable, we need to convert that into anonymous functions, and then we can use capture operator to do that. In this example, we want to pass analyze functions that accept 1 arguments into the stream.map functions. Because analyze functions is a named functions, we need to convert that into anonymous functions using the capture operator. Alright, so that's all about module and functions. Okay, let's continue to documentations. Module documentations. We can create documentation for module and then for functions and also for custom types. But for custom types, we are not going to explore that because it's not being used in the library. For module documentations, we can create that after the definitions of the modules. After this, by using the module doc keyword, add module doc keyword, and then following by the documentations. And documentations in Elixir supports Markdown. For functions, we can also create documentation for functions using add doc keywords. Where we usually put that above the functions definitions. For example, like this. Doc test. So it is a best practice to provide an example inside the functions documentations. The example code can be validated using a doc test when running a test. It ensures the documentation keeps updated, otherwise the test will fail. And doc tests are specified by an indentations of 4 spaces followed by the IEX prompt in a documentation string. IEX itself is an interactive Elixir shell. The test will be run in IEX, and the result from the documentations will be compared with the actual results. And then we can enable doctest by calling doctest Veritaserum command in the test case. So for example, analyze function has this documentation and it has this example. So if we call this analyze functions using this arguments, it should return a list with a value 3 and 5. And then if we call these analyze functions using these arguments, it should return 3. And if this value is not correct, then the test will fail. Function argument documentations. To create documentations for the function's argument, we can use the function's head. From the code snippet below, the function head is the first evaluate functions implementations, which does nothing. It informs us that the function's argument accept word or emoji. So this is the code snippet, and then here you can see there are definitions of functions with name of evaluate underscore and then facet like this. And then if you see there are 1, 2, and then multiple of definition in this kind of loop. So we are going to discuss about these things which called pattern matchings later on. But basically what we are trying to do here is to give argument documentations. So we want to tell that, hey, if you call evaluate underscore facet, you can use word or emoji, right? So we are just telling that you can use word or emoji as the arguments. And then we can define that by using the function head, which the first function definitions that does nothing. If you see, there is no actual function definition here, right? There is no do keyword here. That's the function's head. So that the text editor will show that the evaluate negator functions accepts word or emoji as the arguments. Now let's talk about exdoc. So exdoc is a tool that can be used to create HTML and EPUB documentations for the Elixir project. It will convert all the documentations in the code into a documentations page. So for example, let's open this link. So this is the online documentation for the Veritaserum library, which use exdoc tools. So exdoc tool will analyze the code base. It will fetch all of the documentation in that code base, and it will turns those into this online web page documentations. We can explore about the library. We can explore about all the public functions. Also with the comments and then the sample code and then the link to the GitHub repositories code. And then we can also check the modules that it has. It has two, Veritaserum and Veritaserum.evaluator, which is the submodule. And then we can also check what function that is being exported in the second modules. Right? It has booster list, emoticon list, and so on and so forth. So all of these provided for us automatically by using exdoc.tools. Let's continue to Typespecs. So sometimes it is difficult to find about the type of the arguments or returned functions because Elixir is a dynamic type language. Similar with other dynamic type language, We can add annotations to define the type of the function's arguments and the returns value, which is useful for improving our readability and maintaining the documentation as well, because that will be also visible in the documentation page. And also it enables static analysis tools like Dialyzer. So as we can see here, a functions analyze accepting an input and returning something, right? If we see without the typespecs, right, if you want to know what is the input types and then the returns types, it's not defined here. So we can add annotations like this, telling that, hey, the arguments input is actually can be a list of string or just a single string. And then the return value can be a list of integers or just a single integer. So if you give us a list of string, the return will be a list of integers. If you give us a single string, the return will be a single integer. Data types. Not all data types we are going to cover, just some of data types. So the first one is list. List is a data type that can contain ordered heterogeneous elements. Elixir use linked lists under the hood for their linear data structures. List implements the enumerable protocol. So we are going to check about protocol later. So this is an example of list, right? Use the square brackets to define the list. And let's check about that fact that list is using a linked list compared with other language that usually use array. I have a picture here showing performance in terms of big O notations of array compared with linked list. And linked list excels at prepend element. So why Elixir choose a linked list? Let's continue reading this. So linked lists excel at prepending elements but struggle with random access and appending. This aligns well with common patterns in functional programming, where we often build lists incrementally from the front with using recursions. So maybe it's going to be more clear after or in the discussions of recursions later, right? But if you want to know more deeper about this, you can check on these links. There are two components of a list, head and tail. The head is the first node in the list, and the tail is the rest of the nodes. In the code snippet below shows functions with a list as a parameter. Right, so this is a list of a parameter. However, these functions requires reading the head and the tail of the list explicitly, which use pattern matching to access them. We are going to go there about pattern matching later. So let's check about the simple demo to make it more clear. All right, I have 0 here, new 0, right? And I have a list 1, 2, 3. What I'm going to do is to combine those two into a new list. So the 0 value will be the head and the tail will be 1, 2, 3. So we can do that by using the cons operator. So this becomes the head and this becomes the tail. We can also do similar things like that, combining two lists using the concat functions from the enum modules. So enum.concat combine this list with this list. So it will become a new list. And if you want to access a node by specific positions, we can use enum.add given the list and then the positions that we want to access. And then we can also get the head and the tail from the list. In the example, given this list, we just want to get the head and ignore the tail. Now, let's take a look about map. Map is a key value data type. Like list, map also implements the enumerable protocol. Maps represented by two different implementations based on their size. If the maps with key value pair less than or equal to 32, also called by small maps or flat maps, they are implemented based on a sorted tuple structures, which you can read from this link. Otherwise, if the map has more than 32 key value pairs, which also called by large maps or hash maps, they are implemented based on a persistent hash array mapped trie data structures. So this is an example in the library, which basically it tries to have this string of file locations, which our facets configuration path tries to read that, and then because the file is a JSON, it tries to decode that into a JSON string, which gonna be a key value pair, right? So that will be our map. And then in these functions, facet underscore list, it returns the keys of that map. So we can create map. We can use this percent and then curly branches syntax, and then this will be the key and then the value, the key, and then the value, right? And then we can print the keys of the map with using map.keys, and also we can combine maps, right? We have two maps and then we want to combine them. The same like we combining lists using enum.concat, right? So let's run this. So the first example is to return the keys. So here we're returning the keys of the map, which is in the data type of atom. We'll check about atom later. And second, we are combining two maps into one map, right? So it becomes like this. All right, so next is about tuple. So tuple is a fixed size container for multiple elements. So in this example, we have analyze functions. It returns a tuple, right? With curly branches like this. It's a tuple. This tuple contains two values, score and list with marks. So tuple is usually used for returning a multiple return value from functions like this. There are other use case of tuple. We are going to check that later. And then we can also, let's say, call analyze functions. So we know that analyze functions return multiple value with tuple, so that we can access that by using a tuple 2 on the left side. So this is called pattern matching. We are going to take a look at pattern matching later. Atoms. Atoms are constant whose values are their name. So their name becomes the value. They are often useful for enumerating distinct values. We can create item by using the following syntax: colons atom underscore name. So let's take a look at a common use item here, like OK. So OK is a commonly used item for representing success, and error is a commonly used item for representing error. And of course, you can create your own items. So let's check the common item usage. So first is for the identifier or text, like for in the library, in the Veritaserum library, it used for identifying type of facet. It can be a negator, it can be booster, it can be a emoticon, it can be word. It also used for pattern matchings. We are going to check that later. And also it will be used, or it can be used for a key in the keyword list data types. So other usage, you can check on these links, but let's see for the example. So we have functions analyze underscore mark, and then based on the type, so if the type here is a word, so this is type of facet, right? If the type of facet is word, it returns score. If the type of facet is emoticon, it returns score. And otherwise, everything else will return 0. So we are going to check about case control structure later, right? But that's the example that used in the Veritaserum library. There is limitations. Atoms are stored in the global table, and each atom is unique. And this table will be maintained in the runtime, right? When the program runs. It means that atoms are not garbage collected. So it is advised not to create a dynamic atom. Next, keyword lists. Keyword lists are simple lists. In particular, they are lists consisting of two items, tuples, where the first element, the key, is an item, and the second element can be any value. And there are two ways of creating a keyword list as shown below. So there are two ways, 1 and 2, right? So we can use this way. So this is a list, right? And then keyword list. This is the keyword, and then this is the key, and this is the value. The key need to be an item. Key need to be an item. We can write this with more simpler way, like the right one here, right? Just straight using the key and then the value, key and then value, without using the curly branches, but we move the colons after, right? So we evaluate that this should return true because two of them are basically the same thing. In the code snippet below, the keyword list is used as the last functions parameter. I have functions here, analyze, and the last parameter is actually a keyword list. Because of that, the keyword list can be written without the bracket. So the bracket can be omitted. So this is an example of using keyword lists in pattern matching. What does it mean? Well, we're gonna tackle that later. Do you remember that list and map implements the enumerable protocol? So what is protocol? Protocol is a mechanism to achieve polymorphism in Elixir. We can use dev protocol to define the protocol definitions and use dev IMPL, dev implementations, to implement the protocol for a type. So let's see the example. We have a protocol called enumerable, right? So this is the definitions, and then this is like the functions, right? And every type that want to implement this protocol needs to implement these four functions, right? These four behaviors: reduce, count, member, which return boolean. We know that because this is using a question mark, and slice. If we see the definition here, so def EMPL enumerable, so implement enumerable protocol for this data type, for list data type. And then the implementations of these four behaviors defined in between these two and keywords. The same goes for map data types. Therefore, if we have list and map, we can use every enumerable functions, reduce count member slice, right? We can pass in lists or maps. That's how we use or that's how we achieve polymorphisms in Elixir. Pipe operator. The pipe operator puts the value of the expressions on the left into the first argument of the functions on the right. It makes writing a chain function call look cleaner. So this is the example, right? We have these modules, Veritaserum.evaluator. We have list of word, emoticon, negator, and booster. And then there is a pipe operator here, which is called enum.each. And then if you see the arguments is an anonymous functions. So, oops. So the list will be the first argument of the next functions, which each of these lists call these anonymous functions. And these anonymous functions accept one parameter facets. So these facets will derive from the elements of this list. So for each the iterations, it will create this file path, read the files, and decode the JSONs. So if you see the definition of read, right, file.read, it accepts path. So if you see the path seems like ignored here, but it's not. It's being passed by the pipe operator, right? Again, because the first argument will be passed from the left expressions, right? So the path will be this, and then the results of reading the files, right, will be used for JSON decoding, right? So the code accept two arguments, input and options. Input will be derived from the return value of file.read, and options here is ignored, right? So that's the benefit of pipe operator. And I put a note here. You can see that OPTS and \\/ and then empty list. This is an example of declaring a functions with a default arguments. In this case, options, right? The optional parameters by default is an empty keyword list. So this is another usage of keyword list. So keyword list is used for defining optional parameters. Now you know that. Metaprogramming is the process of using code to write code. It gives us the ability to extend the language to fit our needs and dynamically change the code. Elixir uses compile time metaprogramming. This essentially allows the modifications of the source code before or during compile time, meaning that the generated binary code is slightly different. So the generated binary codes from the compilation time will be slightly different with what we write in the source code. And Elixir has several functions to help us writing metaprogramming. One is code. So just as a binary, which the internal representation of a string, right? An abstract syntax tree, AST, is the internal representations of code in Elixir. And we use it as building blocks for compile time constructs. In Elixir, AST is represented by tuples. These tuples contain three parts. The first one is item, represent the name of the operations. The second one is the metadata of the expressions, and the third one is the arguments of the operations. And if you want to see these AST informations, we use quote. For example, we have expression of 2 plus 3 times 4, and we want to see the expressions in AST. So we use quote, and then if we run the evaluate, it gives us these AST representations in tuple. And after fixing the indentations so that we can see it easier, let's see them in more detail. So the first operation is the plus operations, and then this is the metadata, and then the third component is the arguments. The arguments of the plus operator is 2, and then another operations, another AST represented as tuple, and these expressions is multiply the operations, and then this is the metadata, and then the arguments for this is 3 and 4, and this is the higher order, right? This plus means it is a higher order of the executions compared with the multiplications. So this is the AST representation as tuple in Elixir, which we can access using quote functions. And in another side, there is also functions called unquote, which we can use to modify the AST by injecting code or value. So for example, I have divide functions which accept 42, and then denominator. Denominator is 2. And at the fourth line, I have similar codes, but in this case, the denominator is in unquote. If we call re-evaluate, the third line gives us the tuple of AST, right? The operation name is divide, and then this is the metadata, and then the argument is 42, and the AST of denominator. If we want divide to get the value of this AST, we have to use unquote. So that if you see divide, we'll have access to the value of denominator instead of the AST. Macro. Macro is a function that accepts AST as the input and returns AST. Examples like dev modules, dev, and use, basically they are macros that we have seen so far. Roughly speaking, Elixir compiler first does an initial parsing of your resource code into an AST, and then does another run through in which macros are expanded. Expanding macros is nothing more than running macros on initially generated ASTs to transform them into different ASTs. Let's take a look at the example. There's a thing called unquote fragments, which features to provide an easy way to generate functions on the fly. In these code snippets, we can see that we are trying to generate functions with name facet underscore list, which returns a keys of the map. And then the facets will be based on the elements of this list. So we are going to have eventually functions named word underscore list, emoticon underscore list, and so on and so forth. Let's try to demonstrate the code above with a simple example. So this is the simple example of the code above, right? Which we are going to create uppercase underscore color functions, which will convert the color name in the list into uppercase. And then eventually we will call colors.uppercase blue. If we click that, it returns blue. So this is the example of metaprogramming using what does it call? Unquote fragments. And we can rewrite the same functionalities using macro. So macro helps us to write the boilerplate code once and reuse it in another module. So we have def module color v2, right? And then we define the macro by using def macro. And the macro name is def color, except list. And in this, and the implementation will be, we'll enumerate with map color list and get the access to the element of the list in this color arguments. And for each of the color, we'll do the same things. And then we have a module myColor, which requires colors v2. This is the way so that myColor can use macros defined in colors v2 using requires keywords. And then we basically just call colors v2 dot the macro name def color, and then gives the parameters, give the argument of the list of the colors that you want to use. And then we can call that same as before, myColor dot uppercase underscore blue. So we can run that, and it returns also blue. Pattern matching. This expression x equal 1 in imperative programming language means assign x with value 1, or allocate or update memory for the x with value 1. In declarative programming language like Elixir, x equal 1 means x is equal to 1, like an equal sign in algebra. So in algebra, if we have formula like area equals to br square, it also can be written as br square equals to area, and both expressions are correct. With that in mind, these expressions, x equal to 1 and 1 equal to x, is a valid expression in Elixir. We can say it like binds or labels x to 1. In the context of pattern matching, Elixir match the value on the left hand with the values on the right hand. List pattern matching. So this is an example of pattern matching in a list. This expression means bind or label head with the head from the list on the right, and bind the tail with the tail from the list on the right. It means that if we swap the positions, it remains the same because the value from the left equal with the value from the right. Tuple pattern matching, right? This is an example of pattern matching in a tuple. Analyze functions, return a tuple. Because of that, the left side of the expressions needs to be a tuple too, right? In order to match. Therefore, then we can fetch the score variable or value from the tuple returned by the analyze functions. Function pattern matching. This is an example of pattern matching in functions. We have 3 functions with the same name. Which one will be called? We have analyze, 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 right? Which one will be called? That depends on, first, the number of the arguments that we use, and then in this case it also depends on the type of the arguments. If we call analyze with a single arguments, these analyze functions or these analyze functions can be used or will be used by Elixir. Not this one because it accepts 2 arguments. If the input type is list, then this function that will be used. Because there is an extra check which is called guard. We are going to take a look about that after this, which will give extra check, right? In this case, if the input is a list, then these functions will be used. Or otherwise, this function will be used. If we call analyze with 2 arguments, input and specifically a second argument will be a return keyword list with the key is return and the value is core and max atom, then this third functions that will be called. So this is the example of pattern matching in functions. Guard. Guards are a way to augment pattern matching with more complex check. So for example, I have 3 functions apply underscore booster, right? And the first functions will be called if the word value is greater than 0, right? And the second functions will be called if word value is less than 0, right? Otherwise, which if the word value is 0, the third functions will be called, right? So this is an example of using guard in functions pattern matchings. Guard can also be used in another place, so check these documentations for further reference. Arity, or arity, the number of arguments the functions is to be called with, right? So we have seen these samples before, analyze functions, right? So if you see the first analyze function here have arity of 1 like this. Veritaserum dot analyze /1. It means that these functions with this name accept 1 argument. All right, the same as the second one, but the third one, because it has 2 arguments, the arity will be /2, and that's useful for pattern matching. For example, in the first analyze functions, it will call stream.map function, which the second argument will be analyze functions that we convert into anonymous functions using the capture operator. But which analyze functions? We have 3, right? So in this case, we are going to call analyze function that accept 1 argument instead of this one with 2 arguments. So that's the purpose of arity. All right, we are going to discuss about control structure. I think we are going to discuss 1, 2, yeah, only 2. So the first one is case. To match against multiple patterns, each case clause can match a pattern and execute the corresponding code. So I think we have seen this before, right? This is the case control structures. So if the case is matched, in this case, if the type is atom word, then this function will return score. If the type is emoticon item, it will return score, or otherwise it will return 0. So that's case. The second one is width. So with, it's a handy control for nested cases. If an expression fails to match, the non-matching value will be returned. In the code snippet below, the evaluations will continue until the right expressions does not match the left expressions. So for example, right, this is mark word, and then width, and then it will, if you see, this is tuple, and then this is tuple, right? They are the components of the tuple. The emoji, not emoji, the item, and then the functions call, and then the argument itself, right? The word. So if evaluator.evaluate negator with this word, not returning nil, right? If it's not returning nil, then it will continue, right? Because the evaluation will continue until the right expressions doesn't match the left expression. So if evaluate together returns nil, it will continue. If evaluate together does not return nil, it will stop. It will returns the tuple that whenever it return here. So it will return negator, the value of these functions and the word. If return nil, then continue to the next case, right? Until the end of the case. That's what with does, right? In this case, on the left side, it doesn't check the item. It only cares about the value returned by the evaluations functions. And of course, Elixir has more than 2 control structures like if, else, and cont, and other stuff. So make sure to check them on the links. Recursions. We usually write this code to iterate over a list or array, like this. This approach is not possible in functional programming language like Elixir because of the nature of it. The I variable cannot be mutated because variables are immutable. This is why we need to use recursions. As an example, I have a module called recursions which have 2 functions, count and build. Count will count the length of the list. Given a list ABC, it should return 3. How does it work? First, we need to define the base case. In this case, if the list is empty, just return 0. Otherwise, if the list is not empty, I need the tail. I don't care about the head, so I can ignore the head. And then I will do plus 1 plus count, call the functions again, passing the tail, right? So it will keep continue until the list is empty. All right. And then when the list is empty, it will execute the recursions in reverse order, right? Which will summarize the count, which 1 plus 1 again, plus 1 again, plus 1 again, until all the element has been counted. And the second function is build, which builds a list from n to 1. So if we give a parameter or argument of 3, it will return us a list of 3 to 1 in this order, right? Not from 1 to 3, because the execution will happen in reverse order. In this case, the best case is when 0, we just return the empty list. Otherwise, I need to build a new list where the head is the end and the tail will be from the build functions with the argument of n minus 1, right? And then this is an example of dog test. So if I change this value to 2, right, see that the doc test runs and it tells us that the expected value is 2, but the actual value is 3. So we need to fix that into 3. All right. So now we know why list in Elixir is implemented as a linked list, right? Because prepending element in linked list is only O1 operations. So it's very fast. Tail recursive with accumulator. The recursion examples above are recursive functions without an accumulator. The recursion builds up a stack of calls until it reaches the base case, and then the computation happens in reverse order from the last steps to the first. This is often referred to as post-order recursions. And then we have marked list functions from the library, which written in tail recursive style, where the computations happen during each step of the recursions rather than waiting for the recursive calls to return value. Right, so this is the code looks like. So what we are going to do, we are going to see the steps, walkthrough of the steps of the recursions. So marked list functions, right, accepts a list of words. For each of the words, the functions will call mark word. So these functions will return a tuple of the facet type, score, and a word itself, and the result will be prepended to the result variable. So let's see the walkthrough steps of the recursions. So mark list, with this list, the quality is great. And then the second call will be took the first element, the head, and pass that into mark word the. So now the list only just the tail, right? And then the result will be a tuple of list of tuple of word 0 and the, right? This is the results. And the next call will be take that quality word into the mark word and then combine that with the results. So this will be the head of the list. So that the result now becomes 2 elements of list, keyword list, right? Where the new head is the quality from the quality word. And then it keeps going like that until the list is empty. So when the list is empty, it basically will stop and just return the results. So that's all about recursions in Elixir. Okay, so for the last session that I want to discuss is calling Erlang functions. One of the benefits of building Elixir on top of Erlang is an ability to use Erlang libraries. Elixir can call the Erlang functions using the module name as an item. So the code snippet below, shows a clean functions that transforms the given text with bunch of rules. The fourth rule is to replace an emoticons with a double space 1, 2, right? By calling Erlang functions replace. So like this, colons binary, there's item, right? Item binary dot replace. It means that I want to call replace functions in binary modules that belongs to Erlang. So for example, so here I have a module transformer, and then inside that I have exactly the same like this, right? Which call binary.replace of the text with the emoticon list, right? And then replace that with empty space 2 empty space, and with this option insert replace one. So if we call this wow emoticon, right? This emoticon is in this list, right? And then the result will be wow space space, all right, and then emoticon. So how does it work? So it's basically when you have this string over here, right? That's the string. It will check the emoticon, right? Yeah, I got the emoticon here. It will replace with double empty space. Boom, like that. 1, 2. And then after that, because there is an option insert underscore replace one, it will insert the emoticons back to this, right, with index of 1. So this is index 0, right? Index 0 here, index 1 over here. Put the emoticon back so it becomes like this, right? So there is I don't know, like limitations or maybe a bug on the functions. So because if I give another emoticon right here, if I run that, right, as you can see that the second emoticon is ignored from the transformations, right? Because the functions only replace the first occurrence of the emoticons. So if you want to replace all the occurrence of the emoticons, we need to use a global options like that. Oops, sorry, this needs to be in a list. Right, this is gonna be in a list. Let's go that. All right, so now it works. So this emoticon also, the second emoticon also will be replaced by the double strings as before. Yep, so that's all that I want to share with you. Maybe I will upload this live book markdown to GitHub. If I did, I will put it in the video descriptions. I hope you enjoyed the video. Until the next video, keep learning and stay healthy. Bye bye.